Hello, everyone, and welcome to BrainMap. On this first day of spring, as you know, BrainMap is co-sponsored by the P41 funded Center for Mesoscale Imaging, housed at Martinos. So it is my great pleasure today to introduce our speaker, Professor Nadine Gaab. Nadine Gaab is an associate professor of education at the Harvard Graduate School of Education. Her work focuses on typical and atypical learning trajectories from infancy to adolescence, with an emphasis on language reading development within a learning disability framework. Her work is at the intersection of neuroscience, psychology, learning sciences, neuroscience, edtech, and policy. She is the 2023 recipient of the Academic Research Recognition Award from the World Literacy Foundation, the 2019 recipient of the Learning Disabilities Association America Award, and has received the Norman Geschwind Memorial Lecture in 2020 and the Alice Garcid Award in 2017 from the International Dyslexia Association. Furthermore, she is the founder of Early Bird Education, an edtech platform for the early identification of children at risk for language-based learning disabilities with an integrated professional development platform for teachers. It is my great pleasure to welcome you, and thank you so much for being with us here.
Yeah, thank you so much for having me today. If you're at home or in your office and you want to have the slides, you can scan the QR code. So I'm really honored to be here today. And so the talk I'm presenting today may be a little bit different from what you usually hear at BrainMap, because what we do is very translational. So we see ourselves as a translational developmental cognitive neuroscientist. So I'm a neuroscientist by training. I was at the Harvard Medical School for 15 years before I became a faculty at the ed school. And so now I'm a neuroscientist, sort of a unicorn in an ed school. And so everything we do, which is basic science, federally funded, we always think, how can we translate it back into an educational setting, into a clinical setting? How can we inform policy? And so today you will see both the translational aspect as well as the neuroimaging aspect. I want to start with this quote. So the best way to determine how a child learns is to follow them closely while they're learning. So that seems probably very reasonable to everyone. But if you think about certain skills, it's actually really hard to pinpoint when the skill starts. So I'm asking you, when does reading development start? Right. So if you think about it, just take maybe a couple of seconds and really think, if you had to pinpoint on the developmental timeline, when does learning to read start? Where would you put it? And so usually when I pose the question, I get all kinds of answers, right? So some people say like, well, it's when they first get exposed to letters, and others are like, no, it's when they start formal schooling. And then others are like, no, it's actually a written language. So when they start learning language. And then, yeah, so you can see it's really hard. So if you want to follow kids longitudinally in their skill development, let's say here, reading or any skill development that's, academic, math, social, emotional, where do we start? And so in my lab, we see reading development as starting in utero, because the fundamental milestones for learning to read are sound and language processing, and sound and language processing are starting in utero. And from there, you are starting to distinguish your language from other languages, or your languages from other languages. You are understanding, the sounds that belong to your languages. You are understanding words, the semantics. You're learning the rules, the pragmatics, when to use language. And at one point along the timeline, so usually around maybe 4 years after all this oral language development, someone will start asking you to map the sounds that you've been exposed to and work with since utero onto written graphemes, right? And so when we see reading development as starting at a timeline that starts as early as in utero, if you think about early identification, if you think about, mapping, brain development related to reading, we have to start way, way earlier than, the first day of kindergarten, which has been done primarily in the field of reading research. So after you are, then, mapping the sounds onto the graphemes, you are putting these, sounds together, you're starting to decode single word sentences. And the ultimate goal of learning to read is to actually understand what you read and, read with high automaticity and good prosody. So if you think about this, reading is a really complex skill, right? Starting way, back, in utero at birth. And it takes years to master it. So it's not like, oh, we put someone in kindergarten and within like 6 weeks, they learn to read. No, it's a very prolonged skill. So this is the famous Scarborough reading robe. And so you have two big strands that are important for learning to read, which is the word recognition piece, or what I call the mechanics of learning to read. So how do you actually decode a single word? And then you have the oral language piece, which is also really important because you can be a really good decoder, but if you don't understand the word you just decoded, it's kind of useless, and it will impact how fluently you read and will impact whether you comprehend what you read. So if you think about early identification, if you think about mapping, how children learn to read, we need to think about the, mechanics of actually, reading a single word versus the oral language piece that makes us actually comprehend what we read. So in the US, 67% of fourth graders are reading below grade level, and approximately 80% of fourth graders from low socioeconomic backgrounds are reading below grade level. So we have a reading crisis in this country. And, we'll get a little bit into, how to maybe solve this in a bit. But I want to give you a bit more background on the breadth of the reading problem we currently have. So the impact of learning disabilities such as dyslexia or other reading disabilities is profoundly on social, emotional, and mental health outcomes. So we know that difficulty with developing grade appropriate academic skills can lead to low self-esteem, feelings of shame, inadequately, you have higher risk of anxiety, depression, you often show externalizing symptoms, right? So in a classroom setting, so it has very early on profound implications for mental health. And it makes a lot of sense. Think about a 4-year-old feeling really good about their learning on the playground. They are really fast and good climbers and really good on their bike. And then they suddenly start kindergarten. And everyone around them can map these sounds onto the graphemes and put the sounds together. And somehow you can't figure that out. That has a profound implication for how you see yourself as a learner, how motivated you are to learn, and how motivated you are to go to this institution that makes you do it every day. So you can see how quickly, very early on, pre-KK, we see profound implications in kids who struggle with reading. If you look long-term, we have really strong implications for post-secondary education. Many children drop out if they struggle with learning to read. We see problems with vocational, economic outcomes, and mental health and health in general, because if you can't read, you can't make an informed decision whether you should maybe do this one surgery or the alternative surgery if a doctor hands you two, pamphlets and says, you read about this and tell me what you want to choose. So in terms of struggling readers, there's a big umbrella. Dyslexia is under the umbrella, but not 67% of fourth graders have dyslexia. So you can struggle with reading due to many different reasons. So environmental factors, it has to do with the oral language skills. But if you look at dyslexia, it's about 3 to 12% of children. And it's a specific learning disability with a neurobiological origin. We'll get a lot into this. And it's characterized with accurate and fluent word reading. So if you look at this rope again, so children with dyslexia are kids who initially have problems with the lower part of the rope, the mechanics of learning to read. They may subsequently develop problems with, fluently, reading fluency or reading comprehension, but the core first symptom you see is with decoding single words. And we see a variety of comorbidities or co-occurrences with reading disabilities, such as other, specific learning disabilities like problems with math, dyscalculia, but also anxiety, depression, ADHD, etc. Okay, so what are the factors influencing the development of reading disabilities? So in the 80s, 90s, we were very naive, or maybe not me because I was too young, but thinking maybe there's one causal factor that leads to atypical reading development. And people put all their bets into phonological processing, which is the ability to manipulate the sounds of language. And so it's still a really strong predictor. So it's, I give you some ideas. In 3-year-old, you would probably measure it, give your child 3 words and ask which 2 sound alike, like hat, cat, house, which 2 words sound alike. And then it's developmentally progressing and can get really tricky, like say the word fixed, now say it without the sound k. Right, so you can see, and so this skill has been shown to be a strong predictor of reading, but now in 2024, we know that it's a multifactorial model where you have genetics, brain, perception, cognition, and environment interacting with each other over the developmental timeline, influencing typical and atypical reading development. So if we look at genes, also back in the 80s, 90s, we thought maybe there's going to be a dyslexia gene. Everyone was really excited about this. And now we know there's probably not going to be a dyslexia gene. So we are very certain about this. But there's been some really good large-scale studies suggesting that there are some susceptibility genes. And interestingly, these susceptibility genes are mostly involved in early brain development in utero, giving us an idea that probably some of the problems we see when learning to read stem from way, way earlier than, starting the first day of kindergarten. There's also environmental risk factors. So you have like stress related to, immigration status, caregivers, education, trauma, neighborhood factors. All these factors also contribute to atypical reading development, which can, make it really difficult to like pinpoint, causal mechanisms. So let's look at the brain. So over the last 20 years, there's been, many great brain imaging studies looking at kids who struggle with learning to read versus not, or adults. And we could fairly confidently say that we identified, a set of brain regions, or, maybe a network that is, not, solely doing the, work of, deciphering single words, but involved in reading. And so that involves, for sure, the oral language network, which is not surprising because I showed you on this rope that we have oral language as a really important contributor to, successful reading acquisition. We have the visual word form area, which is, a really interesting area within the fusiform gyrus, which is developing its specificity after explicitly being exposed to letters, right? So it's a really experience-dependent kind of development in terms of specificity. And then we have, sort of inferior frontal regions, what we often call the CEO of the reading network. So these often come on a little bit later in the time course of learning to read, especially when you are integrating what you read into a bigger picture, reading fluency, reading comprehension. So initially, if you look at, pre-K, kindergarten, kids who have been exposed to letters and have mapped the sounds onto the letters, you see this like early, reading triangle where you have oral language, these, sort of supramarginal perisylvian regions, as well as the fusiform visual word form area, being activated and showing changes over time in the first couple of months of learning, to decipher words. We also have, white matter tracts, acrid fasciculus, not surprisingly, as well as inferior longitudinal fasciculus, etc., supporting these brain regions. What's quite interesting is that it doesn't really matter which language you learn to read. So studies have shown that the reading network looks fairly similar, even if you are learning to read in a logographic language like Chinese, or if you're learning to read from right to left or from the bottom to the top. It doesn't really seem to matter that much. The reading network seems to be relatively stable in terms of, regardless of the language you're learning to read in. So in terms of, alterations in children who struggle with learning to read, there's also been many, many great studies in school-aged children showing, reduced gray matter volume in these, areas I just introduced to you. There's, changes in fractional anisotropy in struggling readers compared to, their peers. There's functional differences, et cetera, et cetera. One question that was really important for us to answer is, these brain alterations were primarily shown in kids who already struggled with learning to read. But what we didn't know is the brain changing because you're struggling to learn to read on a daily basis? Or are these children entering the first day of kindergarten with their little backpacks with already a less optimal brain scaffold for learning to read? And that's a really important question for policy, right? So if your brain is changing while you are taught to learn to read, then someone should monitor you very closely while you're learning to read and try to find the pinpoint when you're starting to struggle. But if you're already starting reading instruction the first day of kindergarten with a less optimal scaffold for learning to read, then you should probably be found way before kindergarten, right? If you think about early intervention. So the open question we ask in my lab is, how does learning to read develop starting as early as in utero? How early do developmental trajectories diverge? What's the interplay among learning trajectories, brain development, and environmental influences? Which roles play these factors in the development of learning differences and disability? And who does compensate and how? So the goal here is to move from a deficit-oriented to a preventative model in early education. And so I want to just stop here and explain to you what I mean with this. So right now, what we do in education is we sort of like have the kids start, pre-K, kindergarten, and we sort of like instruct them, but lean back and wait until they show a sign of struggle. And then we react to this and do whatever we need to do. So that could be like, intervention, smaller groups, maybe an IEP, right? But we don't have a preventative education lens like we have in medicine, right? In medicine, we get all these like preventative medicine approaches like mammograms and vaccines and vitamins and checkups, all so that we find problems before they actually cause problems. But we don't do this at all in the field of education. So I'm trying to promote a lens where we move from a reactive to a proactive model in education. And so in order to do this, we need to understand the underlying mechanisms of early brain development and the dynamic interplay between, genes, familiar risk, brain architecture, and environmental influences from the embryo to adulthood. So there are theoretical models explaining the variability in reading skills, and they suggest this dynamic interplay. But the empirical evidence primarily comes from behavioral studies in like kindergarten to 12th grade. But these predictors develop long before kids start kindergarten, and the brain characteristics also develop long before. So brain areas, tracts, network. So learning differences are often not identified until childhood or adolescence, but diverging trajectories of brain development may be present as early as prenatally. So the first study I wanted to show you is a study we did in 2016, quite a bit of time ago. And we were interested in cycle patterns, especially what really was we are mainly interested here was to see cycle patterns are genetically predetermined. So it's basically the topography of the cortex. And so we were really interested if we already see, or if we see differences in the cycle patterns, could that indicate or give us some idea if some of these brain characteristics are already, there way earlier than we thought. And so what we could show here is that especially in this triangle in the posterior part of the left hemisphere, we saw differences in the cycle patterns between kids who have dyslexia compared to without, and also in younger kids, kindergartners, with a familiar risk of dyslexia. So there was one idea that suggested that probably some of these brain characteristics are there, long before kids start kindergarten. And so we started many, many different studies. And so by now we probably have 25, 30 studies that show that some of these brain alterations that we see in third graders or even older predate formal reading instruction. So we could see differences in, FA and the arcuate fasciculus. We could see functional differences in, some key areas that, subsequently, are important for learning to read. We could show gray matter volume differences. We could show, some, using some AFQ techniques in looking at, certain aspects of white matter tracts. So we could, say that some of the brain alterations that we see in children who are struggling with learning to read are already there in 4- and 5-year-olds. And so to go a little bit more specific in this, so this is a study we did with John Gabriele, about 10 years ago, where we looked at, the volume of the arcuate fasciculus, and it's just a, correlation at this point, but with early phonological processing skills, and showing that, the blending or the phonological processing score was correlated with the volume of the arcuate fasciculus. We also looked at, using automatic fiber quantification, looking at, the arcuate fasciculus in greater detail. And we looked at pre-readers, beginning readers, and fluent readers, and this is cross-sectionally here. And we looked at kids who have a strong familiar risk, so who have an older sibling or a parent with dyslexia. And so can we already see differences in the arcuate fasciculus, before they start learning to read, when they begin to learn to read, and, as fluent readers. And so what's important to know here is if you have an older sibling with dyslexia, or you have a parent with dyslexia, you have about a 50% chance to develop dyslexia yourself. So that's very high, much higher than some of the other developmental disabilities. We also looked, longitudinally. So in kids who subsequently develop into good readers and kids who subsequently develop into poor readers, we could show longitudinally that the rate of development in the arcuate fasciculus was faster in subsequently good readers compared to poor readers. But that was primarily done in pre-K. And so we were really interested in, okay, is maybe these alterations that we see early on, is this because of maybe atypical oral language development, right? Because, if we think about the timeline and learning to read starting as early as in utero, maybe there's something, during the first 4 years of learning to read that actually, is interacting with brain development? Or is it something that, it shows up very, very early? And so that's when we started looking in babies. And especially since, you have here different tissue types in different colors, and the, x-axis, you see age of the child, and you can see that the most rapid the period of brain development is happening in the first 2.5 years of life. So we were especially interested in this period. And so we started putting babies into the MRI scanner, and we started this in 2010. And when we initially started this, we were very naive, and we got a grant from the Harvard Catalyst. And we were like, well, we just put these babies in there and they will sleep. And then we look at, brain structure, and maybe, we can get some, functional activation as well if we, give them headphones while they're sleeping. And we miserably failed with the first 20 babies. They would not fall asleep. They would wake up. It was too loud. They would fall asleep on the way to the scanner and would be super awake by the time we had the scanner booked. And so we miserably failed. But so we've been doing this now for 14 years, and we learned a lot. And so we've scanned probably 300-400 babies. And so this is one study. It's called the Baby BOLD study. BOLD stands for Boston Longitudinal Dyslexia Study. So we are enrolling infants when they're between 3 and 8 months old. And they have a strong familial risk to develop problems with reading. So they either have an older sibling or a parent with dyslexia, or they're typical developing. We also scan the parents. And they are basically sleeping inside the MRI scanner. And we mimic whatever, the caregivers do at home in order to, make sure that they actually fall asleep, that we actually can put them in, that they actually stay asleep, and we get some good data. We love having twins because at least one falls asleep usually. And I have a wonderful team of baby whisperers who have been helping us with this. Yeah, and just to show you how long we've been doing this, and we wrote a couple of publications on, how we do this and what are the, main problems with analyzing longitudinal study with a, rapidly growing brain. So this is my daughter here on the left with the little stuffed animal, and she's going to be a freshman in high school this fall. So I can just show you how long we've been following these kids. So the first babies were scanned in 2010. So they're now in middle school, starting high school. And so we followed a lot of them longitudinally. And what we can do now is really look at kids who subsequently develop problems with reading. How, did their brain develop longitudinally, or, at different stages, and what's the role of the environment in these diverging trajectories. We not just only do this in Boston, we do this around the globe. So this is a study we did with Chuck Nelson, where we looked at brain development in Dhaka, Bangladesh. And I can tell you that was very interesting in terms of the sleeping patterns of the babies. It was very interesting for many reasons, but in the US, when you ask caregivers, like, okay, so you're going to come in and your baby has to, fall asleep, and we transfer the baby inside the MRI scanner, or sometimes we put like a MR compatible crib next to the scanner, and the babies fall asleep, and we carefully lift them up. We ask them, like, how does your baby best fall asleep? And you get like hours and hours of like, we have the white noise, and then we have this, and then we rock, and then we have this, and then we have the like lullaby and this breast, and like you get like, and the bouncy ball, you get everything, right? And they know exactly like, well, right now around 9:15, the baby sleeps for exactly 1 hour, and then again at 1:15. So American parents, at least parents in the US, know a lot about how their babies sleep. In Bangladesh, we asked these moms like, okay, can you tell us, because we need to book the scanner, when does your baby, usually sleep? And they say, when it's tired. And we said, well, can you give us some idea? And they're like, sleeping on me, it's on me the whole time. I don't know when they're tired to sleep. And so it was much more challenging to actually get like the good window for these babies to fall asleep. Yeah, so these are, just to show you, again, using AFQ, 4 different, babies, and just displaying the arcuate fasciculus here. The first study we published in 2016 was just looking at, differences in the arcuate fasciculus between infants who had a familiar risk versus not, just cross-sectionally. And we could show in this study that there were certain areas of the arcuate fasciculus using AFQ that we saw differences in kids who had, a strong familiar risk of dyslexia compared to without. And then we looked at this, and this is cross-sectionally for now, like infants, pre-readers, beginning readers, fluent readers, to starting to look at like what could be these trajectories and how early do we see these trajectories diverge. But we have, a lot of longitudinal data. So we started asking questions to what extent is the neural foundation for language in infancy prospectively associated with language and pre-literacy abilities in kindergarten and beyond. And so this is a study, again, using AFQ, where we then looked longitudinally. So we have the brain data, especially the arcuate fasciculus, in infancy, and we then waited patiently 6 years until these babies then started school, and then we could show that the left arcuate fasciculus, like FA, is prospectively associated with phonological awareness skills and vocabulary knowledge, 5-6 years later. And here we controlled for the age at scanning, as well as the amount of home literacy, because we could, in a different publication, show that how often you're read to and how much verbal input you have can lead to these differences as well. We now, looked, now we have, large enough sample sizes that we can, really do, more in-depth analysis. So this is a JAMA paper that just came out 2 years ago, where we showed that, patterns of neural functional connectivity in infants at familiar risk differed from patterns in infants without a familiar risk. Really not just looking at brain structure, but also looking at, resting state. We also have, I didn't put this in this talk, but what we also did is, while the babies were sleeping, we were actually playing them either Dr. Seuss versus an excerpt from the New York Times. And we are also, having some preprints looking at, these functional activation patterns for this paradigm, and see how this relates to, language development over time. We also looked at, functional connectivity in infants and toddlerhood, how it then relates to long-term language and pre-literacy outcomes, and could show that some of these key areas that, we know are, involved in reading, like the eventual visual word form area, that, activation, connectivity in this region with other regions is related to long-term language and pre-literacy outcomes. So we talked a lot about behavior and a lot about brain structure and function, but not so much about the environment. But we have tons and tons of data on the environment. So just to give you an example, so we're really interested in socioeconomic status, parent education, neighborhood factors, schooling, whether they played a musical instrument early on or not, what kind of extracurricular activities they're doing. And one thing we're especially interested is this home literacy environment. And so it has been shown that it is predictive of future language and literacy skills. It can be characterized by, the age of onset of shared reading. So how early do you start reading to your infant, but also how frequently, but also the quality, right? Do you just read the book and then you walk out of the room, or do you actually engage in some dialogue? And so we have a series of papers suggesting that there are strong at least correlations between the home language and literacy environment as well as the arcuate fasciculus in infancy and as well as socioeconomic status. Okay, so the newest part is that we now followed enough babies long enough that we actually can look at these growth trajectories, right? So not just doing some, scanning in infants and then lean back and wait 6 years, but really trying to look at these trajectories. And so our data contributed to this Nature Neuroscience paper that just came out last fall, where they were really looking at, mapping these brain development from birth all the way here, 2000 days of age, and really seeing how does this actually develop? And so this is 2000 infants that were, contributing to this, to these trajectories. And the way we have been doing this, and I strongly encourage you to, invite my senior scientist, Teddy Tereski, who's been doing a lot of the, development of, the methods, especially dealing with these really big problems of, how do we actually quantify development if the brain itself get so much bigger? How do we make sure we can use similar methodology for the different time points, etc.? So for this analysis, we have our brain estimates like white and gray matter volume, surface area, thickness, mean curvature, diffusivity, and we design these using mixed effects models and asymptotic and quadratic functions. We build these individual growth curves, and then we can look at these curve features, so especially the intercepts and the asymptotes, and then relate them back to behavior and build these behavior-dependent developmental trajectories. So I just give you an example here. So we have from our sample, you have gray matter volume or surface area, white matter volume, and cortical thickness. And you can see on the x-axis the age in month. You can see how these trajectories look like over the time course of development. And we have this for, FA and mean diffusivity as well. But where it gets really interesting is when you look at behavior as outcomes. So here on the left, you see the left inferior parietal cortex, and the x-axis is age, and the y-axis is the surface area. And the dashed lines on the top are children who subsequently, when they start school, show really good phonological processing skills. So that's the outcome. And the smaller dashed lines are kids who subsequently show really poor phonological processing skills. So they are at risk, you would think, to maybe develop problems with reading. And we could then, look at these trajectories. And here we see differences in the asymptote on the left, but on the right, if you look at the banks of the superior temporal sulcus, we see differences between these kids in the asymptote as well as the intercept. So these are the things we started to do now to really look at when do these developmental trajectories in kids who subsequently struggle actually diverge. And we think that this is really important for telling us when is it optimal window for intervention, and also giving us really interesting insight in what kind of intervention could we actually develop at that age range. Right? Because we can see what brain areas, show diverging trajectories. We're also really interested in, protective factors, and I'm not getting a lot into this, but some of our kids have a really strong risk to develop problems with reading. They have like 3 siblings with dyslexia, and, if you look at all the multifactors, but they turn out perfectly fine. So we're especially interested in these kids and did a series of studies looking at these kids that are high risk, but subsequently really good readers. What's different in the environment? What's different early on in the brain in infancy that can tell us, what is maybe protective in terms of, brain development? And what we could show is that these kids that are at higher risk and subsequently develop good reading skills often early on seem to have more bilateral processing of language and seem to have a much stronger, corpus callosum in terms of, if you measure it with FA, suggesting that maybe, there is some protective factors early on, maybe genetically predetermined, which then in interaction with a good home environment, like, home literacy, can actually protect these children from developing problems with reading. So the last 5-10 minutes, I wanted to talk about the, culture and framework of translational developmental neuroscience. So we just, this is under review, but we have been trying to see, how can we use the work we do and actually drive, policy changes or, inform educational frameworks. And so here in this paper, we really outline how a partnership between my lab and a grassroots organization that pushed through legislation on Beacon Hill a couple of years ago related to early dyslexia screening in kindergarten, how this partnership was very fruitful in pushing through the legislation. And how did we actually do this as a team under the guidance of developmental dyslexia? So I would strongly encourage you if you're interested in this. But we now have in 51 states in the United States early dyslexia screening legislation. So if you have a child starting kindergarten, 1st grade in Massachusetts, he or she or they will be screened for dyslexia based on some of the behavioral, work that, what people have done, as well as some of the work we've done to inform this. But to summarize, there has been a lot of policy milestones related to reading. So it's not that, politicians have not paid attention to 67% of 4th graders not reading on grade level. So we have the National Reading Panel, we had the No Child Left Behind Act, we have the Individuals with Disabilities Education Act, we have good grassroots movement like Decoding Dyslexia. They actually were on the front of Time magazine, on the front page at one point. We have good journalism. But if you look at the timeline of reading during these policy changes, it's very disappointing. And I'll walk you through this. So this is a test that's done in a representative sample of 4th graders every 2 years in the United States. And you have data here from 1992 all the way to 2022. And it's a very simple assessment. So you read paragraphs and you answer questions about the paragraph. So it's not something like Shakespeare or really, high order. And if these, on average, these fourth graders would be reading proficiently, you would see these bubbles right here on the 240 line where it says NAB proficient. But they are constantly below this each year. So that's where the 67% of fourth graders are now reading on grade level comes from. And so what's really striking here is all these big policies with a lot of funds involved did not move the needle at all since like 1992 at all, right? Also, what's really important is it's not COVID. Right. So I hear all the time, oh my God, like COVID and the kids are not reading well because of COVID. And we should just get them all back to pre-COVID levels. Do you really want them to get back to pre-COVID levels? No, much higher, right? So we had a reading crisis before. COVID didn't do much. And so we don't want to bring them back into the, 2020 instead of 219. So when it comes to learning differences, we are largely focused on a reactive deficit-driven way to fail model instead of the development of preventative approaches. And so what we do currently is, as I said before, we wait, often till third grade, fourth grade before we diagnose someone or, give them access to intensive intervention in the schooling system. But we know that the window for the most effective intervention is much earlier. So what we can do is what has been proposed and now is legislation is to do this early risk screening, similar to you going to your PCP and getting checked for your high cholesterol. And if your cholesterol is high, someone tells you you are at risk to develop problems with your heart, so you better do something preventative so you never develop problems with your heart. And it's the same idea here, and it is now legislation in many different states. And in the slide deck, you have many different information that we put together related to screening, some of the behavioral work to identify what kind of assessments can you screen in 3, 4, 5-year-olds before the start of kindergarten. And we developed a platform called Early Bird Education, which is now in many different school districts around the country. That is a game kids play and has adaptive algorithms telling us who's at risk, and then telling teachers what to do in the general education classroom in order to address this risk. We also work really closely now with pediatricians. So I tell you why, because so we were thinking, okay, so who could do some of this risk screening for learning disabilities? And then we thought, well, pediatricians screen for autism and ADHD, so how come they're not screening for learning disabilities? Pediatricians did not like us and said, well, the reason we don't screen for learning disabilities is because the next step is an educational step. And so we're outside of this. But for ADHD, the next step is often a medical step. And that's why we screen for ADHD and not for learning disabilities. Well, we pushed back saying you should because of the high risk of mental health problems and vocational economic outcomes, depression, anxiety, you should screen. And so then they said, well, we don't, I didn't put it in here, we don't have tools. And so we developed, pediatrician tools so that, soon you can bring your 4- and 5-year-old to the pediatrician, and he or she or they will be screened for learning disabilities. We also do this in the social work world, and try to get this maybe into libraries and other places as well. To summarize, we talked about genetic factors, brain level, perception, cognition, environmental factors that, prenatally, birth, postnatally, could potentially influence atypical reading performance, and really trying to move from this, reactive model to a proactive model and inform the development of, proactive multifactorial models. So the development of reading proficiency is a public health issue. The right to equal education includes the right to read. We really think that we all have to work together in order to make sure that everyone can experience the joy of learning to read. Literacy is a widely recognized determinant of health outcomes and is associated with many indices of academic, vocational, social success. And even the National Academy of Medicine has highlighted the duration of education, which is highly dependent on reading proficiency, is a very significant predictor of health and longevity. Okay, thank you, and I'm happy to answer any questions.